what we're looking at, we just finished up the acids and bases. Now we're going to look at one final class of reactions called redox reactions. Redox stands for oxidation reduction. It just sounds better when we say redox to put reduction first. But we're going to look at the types of reactions that are covered by this oxidation reduction and how to balance equations that are of this type. Up to now, we've had that standard budget type balancing technique, and it works for most equations, but some are more easily balanced if you use this method. And it'll become obvious why as soon as I describe what the types of reactions are. And then we'll finish off with the discussion of electrochemistry, batteries, what causes corrosion, and electrolysis. Okay, what do we mean by oxidation reduction? Any type of reaction where electrons are transferred between reactants to form products, that would classify as a redox reaction. Here's an example where you have sodium metal and chlorine gas are mixed together, and when they react, sodium being a metal likes to give up electrons. That's characteristic of metals. And chlorine being a nonmetal likes to receive electrons. So in this case, the transfer takes place between sodium and chlorine, and now when that happens, we have sodium ion because it's missing an electron, and chlorine anion because it gained that electron. And now the bond is formed between the two, and it's purely electrostatic, a positive attracting a negative. Okay, what we mean by oxidation is anytime an electron is lost from an atom, it's called oxidation. And anytime the electron is gained by some atom, it's called reduction. And they always occur in pairs. You can't have one without the other. Now, remembering what that means, I mean, if you've never done this before or have been exposed to this concept, there's a real easy mnemonic device. It's called oil rig. Okay. Oxidation is loss and reduction is gain. All right, so in this exercise, and when we write these redox reactions, sometimes we leave out parts that are not central to the reaction. In other words, we would call them spectators. They're not involved in the reaction at all. So in this case, we have tin with a 2+ charge reacting with iron that has a 3+ charge. And electrons are transferred. And in the transfer, tin goes from 2+ to 4+, which means, let's do it like this. And we have tin, 4+, and we have iron, 2+. So in order to figure out who lost electrons and who gained electrons, we look at the difference between this tin and that tin. This one had to lose electrons to become more positive. So how many did it lose? It lost 2 electrons for each tin atom. Okay? That means iron had to gain electrons. Okay? So iron gained 1 electron per iron. But notice we have 2 of them. So 2 electrons were gained while 2 electrons were lost. And that's always the case. In a balanced equation, the number of electrons gained have to be equal to the number lost. And we use that to our advantage when we try to balance equations, because we'll balance the electrons first, get those lined up, and then we balance the rest of the equation. And I'll show you the technique in just a few minutes. Okay, so in this case, the 10-2 ion was oxidized. By losing electrons, we have an example of oxidation, which means we have reduction up here. Okay? Now, sometimes, especially when you're given compounds, and then they don't have to be ionic. In this case, they were ionic. Those are the easy ones to deal with. But sometimes compounds are covalently bound. In other words, they share electrons. You don't have complete ions separated from one another, but we still need a way to track the electron movement. And one of the ways we do it is through oxidation states. So we assign what we would consider to be a charge, but it's not really a charge if the atoms are bound covalently, because they share electrons. That's why I call it a bookkeeping scheme. It's just a way of tracking electrons. All right, so here are the rules that govern oxidation state determinations. The oxidation state of an atom when it exists as a free element is 0. Now this is in the most stable state at standard temperature and pressure, which would be standard temperature for non-gases is 25 degrees Celsius. And standard pressure is 1 atmosphere. So in many cases, particularly metals, you would have just the symbol, like mercury. But for some diatomic gases, they may be like that. That is the stable form. And in this case, the oxidation state is 0. And we put the 0 in the place where we would normally put the charge of an ion. In this case, remember it's got 4 positions here, 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 and here. Each one is reserved for a particular type of information. In this case, we're saying that the oxidation state, and actually the charge, would be 0. It's neutral. Okay, that's rule number 1. Rule number 2 is if you have an ion, you've identified an ion with that charge is the oxidation state, +1. Or it could be, say, oxygen was part of a compound, like sodium oxide. In this case, oxygen would have to be 2- because sodium is 1+ to balance the charges. And this would be the oxidation state of that oxygen. Now, if oxygen happens to occur in a covalent compound, like water, right? There are no ions in that molecule. Right? The molecule is like this, with those covalent bonds. So we can't say it's an ion. But when it occurs, oxygen occurs in a covalently bound compound, a molecular compound, we assign it a -2 oxidation state, with one exception. Whenever oxygen is bound to itself in what we identify as a peroxide, like that. And it has something else bound to it. Say, if you go to your medicine cabinet and you find one of those brown bottles, it says hydrogen peroxide on the side. This is hydrogen peroxide. Has two oxygens bound together with hydrogens on either side. In this case, both of them together are -2. So each one is -1. So if we encounter a compound with peroxides, each oxygen has a -1 charge. -1 oxidation state. And these are just examples of different types of peroxides. This is a generic peroxide. This is one where one of the sides is hydrogen, and this could be anything. It could be a methyl group like CH3, or it could be anything. It could be a huge molecule hanging off the end there. The important part is those two oxygens bound together. Okay, when hydrogen is in a covalently bound compound, we assign it an oxidation state of +1. So with water, the oxygen would be -2, and each oxygen would be +1. So a +1 and a +1 balances the -2. We still balance oxidation states. Even though they're not charges, we treat them as if they were for the purposes of bookkeeping. When fluorine is in any compound, whether it's ionic or covalent, doesn't matter. We assign fluorine always a -1 oxidation state. So if you look on your periodic table, not that one, it doesn't have it, but the one that accompanies every review document, you'll see in each one of those boxes, there'll be a list of looks like charges, numbers. Sometimes they're charges, but in many cases, those are a list of the potential oxidation states for each of those atoms, each of those elements. You'll notice that fluorine only has one. It's -1, and that's it. So we give fluorine -1, no matter whether it's ionic, in an ionic compound, or covalently bound. I mentioned this one earlier, but here it is as a rule. The sum of all the oxidation states for a neutral compound must be 0. And then you probably guessed the next one. If you have a polyatomic ion, such as NO3-, that's nitrate, the nitrate ion, oxygen still has a -2 oxidation state. So if we say 2 times 3 is 6, the total oxidation state for the oxygen side is -6. But we have to, when we add nitrogen to it, we have to keep one negative out for that charge. So we really only have to balance 5 minuses with this nitrogen. Since there's only one of them, that nitrogen has to be a +5. And a +5 and a -6 gives you a -1. So in any charged polyatomic ion, the sum of the oxidation states must equal the charge on the ion. Let's try a different one. How about this one? The sulfite polyatomic ion. Oxygen is still -2, so 3 times -2 is -6 total. But we have to hold out. Okay, we have to hold out 2 minuses for that charge. That means we only have to balance 4 minuses. with sulfur. So sulfur is +4. And if, check yourself, total of -6 on this side and a +4 yields a -2. The reason we are assigning fixed oxidation states for some of the elements, like we're doing here, is so that we can calculate the oxidation states for other elements. If you don't have a starting point, like oxygen is always -2, or iron peroxide is -1, or fluorine is always -1, or oxygen is taken as -2, I already said that, then you're stuck. Because whenever those elements are in the compound, you don't know where to start. So this is the way we deal with it, is to assign these values. If you have an alkali metal, right, the first group, alkali metals are always +1. And the alkaline earths, the next door neighbors, the second group over, those are always +2. Oxidation states. They might be charges as well, but we're definitely given these oxidation states, +1 and +2. Okay, there are a couple of others that have fixed oxidation states. For instance, aluminum. Aluminum should always be +3. But it's not as critical to know that one right now. Okay. So we had a couple of examples there. So let's look at this example, which is potassium dichromate. What are the oxidation states for this one? Okay. You can approach this a couple of ways. You can assign, potassium is an alkali metal, so it's always going to be +1. Oxygen is -2. And then you can balance them so that you can find out what chromium is. Or you can split this one out. This whole polyatomic ion is -2. And then you could do that to balance the -2. Let's treat it like a neutral compound. We know that this one is +1, so how many pluses do we have there? We have +2. Right? Here we have 7 times -2 for oxygen, which is -14. Okay. What do we have now that has to be balanced by chromium? Add these together in -12. Okay? So these two chromiums have to balance that -12 with a positive oxidation state. Well, we've got 2 of them. We need +12, but we've got 2. So that means each one is +6. So that is the oxidation state for chromium in this compound. Okay. How about the next one, the polyatomic ion carbonate? Okay. Now we know we have to balance oxidation states to give us the 2- value. Oxygen is -2 times 3 is -6. But we need to keep 2 minuses out. Don't balance those 2. So that means we only need -4 balanced with this carbon, which means +4. Okay. How about the next one? MnO2. Right? Oxygen's -2, which is -4. This is a neutral compound. So this manganese has to balance that -4 with a +4. Okay. PCl5. That is a covalent compound. They're both nonmetals, which is pretty sure that they share electrons. Chlorine, we weren't given rules for chlorine. When you find chlorine in a compound like this, assume that chlorine is -1, just like fluorine, the halogens. If we don't do that, then we're stuck. We can't go any further. So we have to assume that chlorine is -1, which is -5 total, which means +5 for phosphorus. Now, if chlorine is in a compound with another halogen, like bromine, then you take the more electronegative one and fix that one. Like if we had maybe something like that, bromine dichloride. Since chlorine is more electronegative, we'll fix its oxidation state at -1. So -2, that means bromine would have to be +2. That's how we get around that problem. Okay, let's see. We got one more example. SF4. This one's easy. We have a rule for fluorine. Fluorine is always -1. So we can do this one without looking at the board. Fluorine is -1, so 4 of them are -4. That means one sulfur must be +4. Okay. Okay. We assign oxidation states here to the neutral atoms, neutral elements, 0 and 0. And then over here, we have charged species. So those charges are the oxidation states, +1 and -1. Okay. Sodium is oxidized. Now, since they always occur in pairs, oxidation and reduction, then the one that is oxidized loses electrons, and it sends those electrons to the other species that is reduced. So that means the oxidized one is the reducing agent. It's the one that causes reduction in the other atom. Okay? So if sodium is oxidized, it's the reducing agent. So that means that chlorine is reduced. That means it is the oxidizing agent. All right. Now here's one. Is that true? Let's see. CH4 gas plus O2 gas yields CO2 gas plus water gas. Okay, they've already balanced the equation for us. All right, so how do we know that carbon was oxidized? Right? Oxidation is loss. Oxygen, carbon must have lost electrons. Let's see if that's true. What's hydrogen? The rule is hydrogen is +1. So that means +4 total. That means carbon has to be -4 oxidation state. On this side, oxygen is -2, which means -4 total. That means one carbon has to be +4. So if carbon goes from -4 to +4, it definitely had to lose electrons. How many electrons? Well, how many would it take to go from carbon -4 to carbon 0? It would have to lose 4 electrons. 4 electrons to 0, and then 4 more electrons to +4. So in the process, carbon had lost 8 electrons for each atom. Okay, that means oxygen had to be reduced. It had to gain electrons. So where did it go? Well, it went 2 places. Right? It went from here, 0, here's -2, and here's -2. So it went here, and it went here. So this 0 went from 1 oxygen had to gain 2 electrons. Gain 2 electrons per oxygen. But there are how many oxygens? Well, there are 4, right? There are 4 electrons. Excuse me, 4 oxygen atoms. So that equals 8 electrons gained. And this is times 1, which equals 8 electrons. So the gain and the loss of electrons balance. That makes this molecule the reducing agent. It causes reduction of oxygen. And since oxygen was reduced, it is the oxidizing agent for methane. This is methane. Okay. All right, just a review. Sometimes you'll see it referred to as oxidation is an increase in oxidation state. So that means it becomes more positive. So it starts out at -4, then it becomes more positive toward -3, -2, -1, 0, +1, +2, +3, +4. It's becoming more positive. That's oxidation. And reduction would be a decrease in oxidation state. It becomes more negative. So in this case, it goes from 0, -1, -2. Okay, let's see if we can, I mentioned earlier, but I'll say it again. Some reactions do not transfer electrons. In other words, they are not redox reactions. So let's see if we can identify which of these are redox, and maybe one or more of them are not redox reactions. Here's a clue. This is a rule of thumb. If you have a neutral atom, an element on one side, either a reactant or a product, doesn't matter, then you look to the other side of the equation. In this case, we have that element on the reactant side. Look on the product side. Where is it? It's in a compound. If that element enters a compound in the product, you have had oxidation reduction. Or, in this case, if the element hydrogen is in a compound on the reactant side, now it's a neutral element on the product side. That's also an indicator that oxidation reduction has taken place. Right. We can go in and then calculate. Right. Zinc is a 0 here, and over here is a +2. So that's evidence there also. That's quantitative evidence. the rule of thumb or qualitative evidence is just what I said. It's an element here, it's in a compound there. That's oxidation reduction. Okay, there's one. How about this one? And we can't use the rule of thumb on this one. We have to actually calculate oxidation states for each of the elements. So if we do that, oh, I see, I left out a part. Which one is the reducing agent? Well, zinc lost electrons. It was oxidized. That makes it the reducing agent. And HCl, in this case, the hydrogen in that molecule gained electrons. It decreased its oxidation state from +1 to 0. So it is the oxidizing agent because it was reduced. Okay, oxygen is always -2. There. Hydrogen's +1. And there's another oxygen, and hydrogen. Okay, so let's see, what happened to oxygen? Oxygen, nothing happened to oxygen. So oxygen's not involved in the oxidation reduction part of this reaction. Hydrogen stayed the same also. So what's going on here? Chromium is +6 here, right? 7 times -2 is -14. We hold out 2 negative charges for the ion. That means -12 has to be balanced by 2 chromiums. Each one has to be a +6. Then we go over here and check that one out. 4 times -2 is -8. We hold out 2 minuses for the charge. That means a -8. -6 has to be balanced by the chromium, only 1 chromium. So that chromium has to be +6. No oxidation reduction has occurred in this reaction. How about the next one? Okay, the element copper is 0. This chlorine is a -1. This chlorine is a -1. Right? So chlorine was neither reduced nor oxidized. This copper is +1. What this copper is is 0. So copper could have been what? Reduced. We added an electron to it. It gained an electron. But what about that copper is +2? So what do we do? That copper, to go from here to here, would have lost an electron. Okay? This really happens. I mean, this is true. We've got to explain it, right? Nature just does what it does, and we have to figure it out and explain it. In this case, we have a reaction called disproportionation. That is, this 2 says there are 2 of those molecules of copper 1 chloride. One of those coppers is oxidized and the other one is reduced. So it would be like writing your equation this way. Now it's easier to see. This one is +1 here, +1 here. Over here, it's +2, and here it's 0. So one of them could go like this, and the other one could go like that. Okay, so this one would be oxidized. This one would be reduced. Okay, simple explanation. This is used by the mining industry to prepare copper from this type of ore, Copper occurs in several types of compounds in the rocks you dig out of the ground. This is one way to get copper out. You just heat it up. Well, this is an aqueous solution, but you can do this as a powder. Just throw it in the furnace and heat it till it's really hot, and you get this reaction also. So both of those were oxidation reduction reactions. And in this case, this one was the oxidizing agent and the reducing agent. And both of them. Actually, one of those molecules was one was the other. That's the best way to look at it. Okay. Now that we know how to assign oxidation states, how to identify species that are oxidized and where they go, and the reduced and where they go in the products. Now we're going to use that information to help us balance equations. In order to balance a given equation, you have to split it into two, called half reactions. And in one reaction, you only put the species that are being reduced. And the other one, you put the one that's being oxidized, what it ends up as. Okay? So here's an example. This one already has everything that's involved in the reaction there in the equation. Right? This is just to show the end product, so to speak, and how we got there. So 8 protons means what? That's an acid. We learned in the last chapter that these protons never exist like this in free. They're not free like that. They're always combined with water or the acid they came from. But for convenience and for ease of manipulating the equation, we're going to consider these protons separately, just like that. This ion is there, the manganate ion. This ion, the iron 2+ ion. Then we get, as product, we get the manganese 2+ ion and the iron 3+ ion and water. So water is a product of this reaction. And it makes sense. There's oxygen, there's hydrogen, they make water. Okay, now what are the half reactions for this balanced equation? Well, we have to identify which is oxidized and which is reduced. There we go. Those are all the oxidation states for each of the species here. +1, +7. Manganese goes from +7 to +2. So it was decreasing oxidation state means we added electrons. Iron goes from +2 to +3. It lost electrons. It was oxidized. Hydrogen didn't change. Oxygen didn't change. They're part of the reaction, but they're not part of the oxidation reduction. Okay? So the reduction includes these species, and the only reason that water is there is not because it's reduced or oxidized, it's because it was formed from this hydrogen and that oxygen. So it has to be there to balance this half reaction. But notice what we've added. In the half reaction, we actually show the electrons. So if manganese goes from +7 to +2, and there's only one of them, then we had to gain 5 electrons. So the 5 electrons would be on the reactant side, because they were absorbed into this manganese, and now the manganese has a reduced oxidation state. So if we look at the oxidation side, that leaves just iron and the electrons. So if this iron is oxidized, it loses electrons, and now these electrons show up on the product side. Okay, so that's what it would look like as a balanced half reaction for each one. What we want to do is take an unbalanced equation and reverse this procedure and balance it. So here's how we do it. There are two types of redox reactions that we can identify. They don't always occur, but when they do, they'll either be acidic or basic. There are some redox reactions that do not involve acids or bases. But this is where you start. This is the acidic method. And then once you balance the acidic method for an equation, if you know it occurs in basic solution, then you modify it so that it will be show the base in the balanced equation. All right, we'll do that in just a few minutes. But here's what you do. You identify and write the equations for the oxidation and reduction half reactions. So to do that, you have to know the oxidation states of each of the elements. You have to identify which one is the oxidation half reaction, which one is oxidized, then which one is reduced, and set those apart in separate reactions. We're going to bring them back together later, but we have to balance them as half reactions first. Now, when we do that, we balance all the elements. Actually, that's true. We balance all the elements except the hydrogen and oxygen. Don't bother with those. Say if there's iron in there, if there's tin in there, if there's chromium, whatever it happens to be, part of the oxidation and reduction half reactions, you balance those first and don't do the hydrogens and oxygens yet. Then once you get those elements balanced, you balance the oxygen using water. So if there's oxygen on one side, but it's not on the other, you put water molecules on the other side to balance the oxygens. And then you balance the hydrogens because you added water with hydrogen in it. Now you got to put hydrogens on the other side to balance the hydrogens. And you do that in acidic solution with protons, H+ ions. Now, once that's done, then you take the oxidation states, after you've got all those things balanced, then you assign how many electrons will transfer. In the oxidation half reaction, the electrons will end up on the product side. In the reduction half reaction, the electrons will be included on the reactant side. Okay. Now, what do? Before we can combine the two equations back together, the electrons have to be balanced. They have to be the same in each reaction. So if they're not the same, you multiply one or both of the equations by some value all the way through the equation, the half reaction, so that you get the same number of electrons in each one. Right? That satisfies the condition that the same number of electrons that were the product of oxidation were supplied now for reduction. Okay. Once that's done, then you can add the equations back together. Now I'm going to show you an example and call out all these rules as we go. Okay. So here's our example. Let's do this. CR2O7, 2 minus. I'm going to leave out the aqueous. Everything's aqueous. Right. So I'm not going to put that in there right now, just so I have more room. And then we're reacting that with sulfite to yield chromium 3 plus, and then sulfate. Okay, that's our unbalanced equation. Right. First thing we need to do is assign oxidation states so we can tell which one is the oxidation half reaction and which one is the reduction half reaction. So, well, the easy one is this one. That's the oxidation state. On this side, we have a 2 minus, or minus 2 for oxygen, which is minus 14. We have to hold 2 of those with this charge, so minus 12, and 2 chromiums means plus 12. Each one of these is plus 6. Okay? We did this one before, I think. 3 times 2 minus is minus 6. Hold 2 out for that one. And this one is plus 4. We have minus 2 times 4 is minus 8. Hold 2 out, minus 6, plus 6. Okay. There we go. Now, oxidation, half reaction. Which one was oxidized? Which one lost electrons, became more positive? Sulfur. So the oxidation half reaction puts sulfite with a plus 4 here and yields sulfate with a plus 6. Okay? The reduction half reaction then would be dichromate with a plus 6 oxidation state on the chromium and the chromium 3 plus ion. Okay? Now we've got our half reactions separated. First thing we do is balance elements that are not oxygen and not hydrogen. So 1 sulfur, we're good. Here we have 2 chromiums and only 1 here. So that's 2 chromiums. Okay. Now we balance oxygens with water. Okay. We have 4 oxygens here and 3 there. We need 1 more oxygen over here. Okay. We have 7 oxygens here and none on that side. So we need water here, but we need 7 oxygens. Okay. Now we balance these 2 hydrogens with protons on this side. 2 hydrogens, 2 hydrogens. Here we have 14 hydrogens. Here we go. So now we have 7 oxygens here and 14 hydrogens here. Those are balanced. Okay. Next thing we have to do is balance the electrons. So we have an oxidation state here of plus 4, and there's a plus 6, which means we need to add electrons on this side. How many? Well, we went from plus 4 on 1 sulfur to plus 6 on 1 sulfur. We only need 2 electrons because 2 minuses and a +6 equals a +4. Okay? On this side, we're reducing. So we need electrons here. How many? Well, we went from a +6 to a +3, which means we had to add 3 electrons per chromium. But there are 2 chromiums. So 3 electrons times 2 is 6 electrons. Okay? Now, we have to balance the electrons before we can bring the equations back together. Here we have 6 electrons, here we have 2. So we need 6 electrons in this equation. We multiply the whole thing through by 3. Now let me do it this way. Okay? So what does that do? That puts a 3 here. That puts a 3 here. 3 here. A 6 there. And a 6 there. So now we have the same number of electrons, plus our coefficients are changed to match, and we can add the equations back together. All right, let's bring down the reactant side. Three sulfite. We have 3 waters. And 14 hydrogens plus 6 electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now let's bring these down. Okay, 3 chromiums plus 3 sulfate. I have to wrap around here. Then we have 7 waters, 6 hydrogens, and 6 electrons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, that's everything brought down. Now you cancel. If you have the same thing on both sides, then you look at how many of each there are. So, waters. There's 7 on this side and 3 on this side. So these waters are gone, and we're left with 4. Hydrogens. We have 6 on this side and 14 on this side, which makes 8. And the electrons cancel. Okay? So now we have 1 dichromate ion, 3 sulfite ions, 8 hydrogen ions, yields 2 chromium 3 ions, plus 3 sulfates, plus 4 water. That's it. So here it is shown in steps. I thought it was better to do it on the board, but here it is in animated form. And we should end up with on the next slide, I think this is it. Not yet. There we are, combined equations. There we go. Nope, still not done. There we go. There are the waters And there's the rest. So that's 8 hydrogens, 1 dichromate, 3 sulfites, yield 4 waters, 2 chromium 3+ ions, and 3 sulfate ions. Okay. I know it's a lot of work, but what I'm going to do now is, since we already have this one on board, this one is in acidic solution. Suppose we know that this reaction takes place in basic solution. How do you deal with that? Once you get to this point, then to make a basic solution, let's see, let's clean it up a little bit. Let's put the 8 down here. Get rid of that water. Get rid of those electrons. Let's make this one 4. Get rid of those, get rid of those. There we go. How do I make this basic solution? What you do is you add hydroxyls, OH minuses. And how many do you add? You add enough to neutralize that hydrogen ion. So if we add 8 hydroxyls here, we have to add 8 hydroxyls on this side. Okay? Do the same thing to both sides. This makes what? 2 hydrogens and 1 oxygen. This makes 8 waters. But now we have 4 over here and 8 over here. Those are gone. And now we're left with 4. So this is in basic solution. Now we have these same species, but we have water on this side, hydroxyls on that side. And remember, in these balanced equations, everything is in the same mix. They're all together. So if we show it over here like that, that's for the whole equation. We are in basic solution now. Okay. All right, so let's see, what do we have next? Okay. Here's an example of a redox reaction, and we know it's redox. Look, cerium 2+, cerium 3+, cobalt 2+, cobalt metal 0. So we know this is a redox reaction. What's the coefficient in front of the cerium 2+ over here? Notice that there are no extra oxygens in there. There are no extra hydrogens. We're not going to have to deal with this as adding protons or waters, hydrogens and oxygens. Oh, they're not going to show us. I have to do this one on the board, I guess. Yeah. Well, you know, we may not have to use half reactions here. I mean, half reactions will work, no doubt about it. But this is a shortcut. Cerium 2+, cobalt 2+, cerium 3+, and cobalt metal. So this one's 0, 3+, 2+, 2+. Okay, which one's oxidized? Cerium goes from 2+ to 3+. It's increasing oxidation number. It is oxidized. loss 1 electron per cerium. Cobalt, reduced, gain 2 electrons per cobalt. So if we got 2 electrons gained here, we've got to have 2 electrons lost there. So how would we get that? Well, if we say 2 ceriums, then that would equal to 2 electrons. And that is the answer. That equation is balanced. Let's see. Come on. There we go. Okay, so the coefficient here is 2. We didn't have to go through the half reaction process to do this. We could have, but we didn't need to. Now this one, the clue here that you need half reactions with the full gamut of rules is that there's an oxygen here and it doesn't show up on the other side. We've got to account for it somehow. So this one, we would have to separate into half reactions. We just need to find out what the oxidation states are so that we can separate it. Manganese goes from +7 to +2, which means it is reduced. Its oxidation number decreases. Whereas bromine goes from -1 to 0. It increased from -1 to 0. It gained electron. So if we separate them in two, right? This one is the reduction. This one's the oxidation. Okay. We just need a 2 in front of this one to balance the elements other than oxygen and hydrogen. Okay, this one's out of order. I'm sorry about that. This electron should have come after the oxygens. Okay. Unfortunately, it works. So now we put 4 oxygens on this side to balance those 4. Now we need 4 hydrogens on this side as protons. And here they are. 8 hydrogens to balance those 8. Okay. We didn't have to do anything with this one except to balance the electrons. Now we need to, we've got 5 electrons here and 2 electrons there. We can't add those 2 equations together. Not yet. So how do you get an odd and an even to balance? Cross multiply. Multiply this one by 2 and this one by 5. Okay. That means you'll have 10 electrons here and 10 electrons there. Now we can add them together. After we cancel things out, excuse me, back up, here we go. Let's see. Yep, that one. And then you look at your equation, what you think is balanced equation, and say, is it possible to reduce it any further? Well, that's 2, 10, 16, 2, 5, and 8. Right? So we can't reduce it any further to the simplest whole number ratios. Okay. Now, if we take this one and do the same thing to it that we did before and convert this to a basic solution, then we would neutralize those hydrogens with hydroxyls. We need how many? 16 hydroxyls here. Put 16 hydroxyls on that side. Okay. And then 16 hydroxyls on that side. Add them together, we get 16 waters over here. And now we have 8 waters and 16 hydroxyls on that side. Okay, now we cancel. Since we have 8 waters on this side and 16 on that side, those cancel out and we're left with 8 on the reactant side. Okay, so that would be our balanced equation. There we go. That's our balanced equation in basic solution. Okay. So now that we know this much about redox reactions, what's electrochemistry? Electrochemistry refers to the exchange of chemical and electrical energy. So most chemical reactions proceed because they are more stable as products than they are as reactants. And the energy transfer sometimes can be tacked. You can intercede and extract and use that transfer of energy. In this case, the transfer is in the form of electrons. When those electrons move, if there's some way that we can get hold of those electrons while they're moving, we can extract energy from them. In the first case, I mentioned just now, we want to take those moving electrons and use that energy to do work. When you think of this type of electrochemistry, think of batteries. That's what batteries do. They take a chemical reaction and they send the electrons out of one side of the reaction into the other side. So the two parts of the battery are half cells or half reactions. So we take one half reaction and we send the electrons not directly into the other half reaction, we send it externally so we can tap it on the way as it goes to the other half reaction. The other way is just the reverse. If we drive electrons from an external source through one half reaction, then it can produce, it's actually, you take the balanced equation and flip it, just reverse it. The spontaneous reaction is the one from left to right that we've written so far. But if you have an external source of electrons that you can drive into that reaction, you can make it go backwards. So these are actually inverse of one another. Okay, first one. The electrochemical cell is also known as a battery. For this reaction, we're combining these two half reactions. Right? This manganese, which should be at +7 oxidation state, and this one is +2. So manganese is being reduced and the iron is being oxidized. And the electrons that are transferred from this reaction, from this species to that species, have to go through an external wire. Those electrons are transferred, let's see, actually from this side to that side. And if we separate the half reactions like this, keep them apart from one another, then the only connection they have with one another is through the electrons. The problem is that in all electrical circuits, there must be a complete movement of electrons and ions between the two. It's got to be, that's why they call it a circuit, because it goes in a circle. So this is okay for now, but there's no reaction occurring, right? We cannot move electrons here because we have a broken circuit. But we can identify that this one is the electron donor, the reducing agent, and this one is the oxidizing agent or the electron acceptor. Right? We've got that established. And we keep those reactions separate from one another. If you just put them together in the same solution, the reaction goes, but you don't have access to the electrons. That's why we run them through an external wire. So how do we complete the circuit? Well, if we don't do it that way, then the electrons build up on one side. You get, and they are depleted on the other, and you build up an electrostatic charge to a certain point. So in order to complete the circuit, we need a way to bridge the gap between these two solutions so that the electrons and the ions, the charges can move in a circle. Now the electrons are only going to go from here to here. So we need something else to carry the charge to complete the circuit. And we do that by making a connection here. Sometimes we use this device called a salt bridge. It allows for ion movement between the two. As long as you've got ions moving, you can complete a circuit and current will be shown in any measurement in that wire. So you can measure using an ammeter or a multimeter, you can show certain amperage. In other words, movement of electrons through that wire. But it only occurs when you have this bridge in here, some connection, or the other option is a porous disk. What the porous disk is it allows enough space through the disk for ions to move. Now, electrons don't move, not through here, just the ions. I guess technically speaking, if a negative ion moves, then electrons move. But this porous disk is actually more efficient, right? There's more resistance here to movement of ions, here, than there is here. But that completes the circuit. There's another name. Electrochemical cell or battery is also a galvanic cell. And that's named after the Italian Galvani, who was the first person to invent the battery. Actually, he called it something else. It was a pile, because he piled copper and zinc, I think, discs, one on top of each other, and in between each one, he had a piece of cloth soaked in some salt. He stacked them together and connected the opposite ends through a wire, and if you grab it, you get a shock. So that was the first battery. Okay, back to the topic here. So we're converting, in this process, we're converting chemical energy into electrical energy by this device. Now, when electrons move this direction, then we have to maintain the balance of charge. And we do it by, if you're increasing the negative charge on this side, then those negative ions have to move this way. And some of the positive ions also have to move this way. Everything is a balance. You don't have any built up electrostatic charge in this process now. So whatever is required, negatives move this way, positives move the other way, just to keep things balanced. Now we have names. So when we build these cells, the anode is on the side where oxidation takes place. So if our species goes from +2 to +3 iron. Oxidation takes place at that site. That is the anode. The other side, where reduction takes place, on this side, where the manganese 7+ goes to manganese 2+, we have added electrons to the manganese, which means it's reduced. And at this side, reduction has taken place. That's the cathode. It's always that way. Reduction means cathode, oxidation means anode, always and forever. Okay. All right, that's an electrochemical cell. And if we know other things about those half cells, like what are the electrodes sticking down into the solution? What is in the solution? What concentrations are they? Then we have a way that we can actually calculate the expected voltage that's produced in that external wire. But that's beyond this course. This just introduces the topic. And we're not going to do that in this class. So the other process, where we go in reverse, we take electrical energy and convert it into chemical energy. We produce a chemical change with that external electrical source. That's called electrolysis. The key word here is non-spontaneous. In other words, the reaction we want to occur will not occur on its own. We have to force it by putting energy in the form of electrons. So we push electrons in there, and they cause the chemical reaction to go in the non-spontaneous direction. Okay, example. Cars used to have heavy steel bumpers. Right? That's how they protected themselves in a crash. They didn't have the hydraulic pistons to where the bumper would move when you strike something, and they weren't covered in plastic. But they weren't left as that ugly steel. They were actually coated in chromium, which made them shine. So chrome plating bumpers is an example of electrolysis. Instead of the chrome being oxidized from 0 oxidation state to maybe 3 or 7+ or whatever the case may be, we go the other direction. And that the site where chromium goes from a positive ion to 0, we make metal on that object. We are reducing the chromium. So the bumper is the cathode. That's where reduction takes place. That steel bumper is the cathode. And then there's an anode in the solution where oxidation takes place. And we drive electrons through the bumper so that we can reduce chromium ions in solution and plate them on the bumper as chromium metal. That's one example. Here's an example of a battery that almost every automobile now has under their hood. If it's a gas-powered engine, it's not a hybrid, and it's not totally electric, then it will have one of these batteries in it, the lead-acid battery. Of course, if it's completely electric car like a Ford Volt or a Tesla, it'll have lithium-ion batteries. But if it's gasoline-powered or a diesel-powered engine, then it'll have a lead storage battery. Often we call it a lead-acid battery. And the reason we call it lead-acid is because the solution in that battery is sulfuric acid, and it's very high concentration. So it's a dangerous solution. You don't want to get any on yourself. Batteries used to have caps in them. You pull the cap out and you'd stick a tube in there to a device and suck some of it up into your device, and it would measure the specific gravity of the sulfuric acid in your battery. And you could tell from the specific gravity of the solution how concentrated it is and whether it was depleted. Most service stations that were full service would do that for you while you filled up with gas. Now the batteries are more or less sealed. In other words, you can't access them internally. There's some other chemistry going on there that makes that unnecessary, which is a good thing. But here's the reaction. So we're taking lead and sulfuric acid at the anode where oxidation takes place. And we're oxidizing this lead zero oxidation state to this lead, which is 2+ oxidation state, or +2. And there's the half reaction. At the cathode, reduction is taking place. So at the cathode, this lead 4+ or +4 oxidation state is going to the lead 2+ oxidation state. So there we are adding electrons to this one to make that one. Okay? Notice that what we have here in common is sulfuric acid on both of them. So this is one case where you don't need to separate the half cells. They can share the same solution. All you need is a separate lead electrode on one side and a lead oxide electrode on the other side with a solution in between, and the battery will work. You don't have to have that salt bridge or a porous disc to make it work. Right, so each electrode is submerged in this sulfuric acid, and the reactions occur independent of one another, and we send the electrodes outside to do work on their way to the other side. Now, each one of these cells, let me see if that's part of the slide. I don't want to steal my own thunder. Okay. Yeah, let's go to the next slide. So this is what the battery looks like. One of these plates, this one is lead oxide, lead 4 oxide. So this is the cathode. And we produce lead sulfate. Lead sulfate is insoluble in this solution. So it coats the electrode where the reaction occurs. Same thing on the lead plate. The anode, lead sulfate, coats that plate. So when we start our engine and the alternator begins to run and it produces a current that runs in reverse, then it drives these reactions backwards. So over the course of operating your automobile, you begin by using it as a battery. Right? It produces an external current that turns your starter motor and gets the engine running. And once the engine's running, then it runs the current backwards and turns this into an electrolytic cell. It reverses the reaction. It's called recharging. We've recharged the battery that way. And we drive the reaction backwards. Okay? Now, the problem is this lead sulfate is coating those plates. If you don't completely use up all that lead sulfate, and sometimes it gets down into the microscopic cracks and doesn't have access to the solution outside, so the reaction doesn't occur. Okay. So over the years of charge, discharge, charge, discharge, you build up this lead sulfate on each of those plates. And at some point, it's so thick that the plate can't access the solution. And at that point, the battery is dead and cannot be recharged. And the term for that is, we call it, the battery is now sulfated out. And the only way to recover it is to send it back to a recycling site. They'll take it apart and do some chemistry and separate the components and sell their products to battery manufacturers. Okay. The other thing that's interesting is, if you ever look under the hood at your battery, you'll find that they still have those caps on them. They're just not accessible. You may be able to see how many ports there are in the top of your battery. There should be 6 of them. You have to chain 6 of these cells together from internal battery. So they're actually separated in the battery, separate. This one produces 2 volts. This one produces 2 volts, 2 volts, 2 volts, 2 volts, 2 volts. And they're in series. So they're additive. So 6 times 2 volts each is 12 volts. So the battery under your hood, most cars, is 12 volts because we chain those cells together. That's how you increase the voltage of output. And if you have one of those little 12-volt batteries with the electrodes on top, internally, it has multiple cells built into it so that you can get the 12 volts out of it. Okay. So what we call electrical potential is also identified as voltage. Electrical potential can be viewed as the push. So what is pushing those electrons from the anode to the cathode? It's the voltage. It's the push of the reaction that's driving those electrons from one side to the other. It can be thought of as pressure, okay? or just a force that's driving it, and it's measured as volts. This is called electrical potential. Oh, I forgot I had this statement in here. This is true. If you need higher voltage, you can take those electrochemical cells, those galvanic cells, and chain them together. And as long as you have one battery here with an electrode there, say this is negative and this is positive, and you chain them together so that you have negative, positive, like that. Then you connect them like this, and they can keep going like that. Then when you put them in series, they add voltage. You total the voltage of each of the cells. So theoretically, you could make 1,000 volts if you had enough batteries together and just put them together, and you could build up a huge charge. It'd be dangerous, but could be done. Okay. The batteries we've talked about so far have a liquid, what we call an electrolyte. The electrolyte is the solution in each of the half cells. But there are forms of battery that stabilize the solution in a more or less solid matrix. You still have ions that are able to move, and electrons can move, but it's more stable. It may be a gel, it could be a paste, and we call those dry cells. They're not really dry, right? A dry cell won't conduct electricity because the ions can't move. But a dry cell is the term that we use for it. They just don't contain completely liquid electrolytes. that could spill if you dump it over one. Pull the cap off and turn it upside down. Some are acid versions and some are basic versions. Here's an example, right, where we have ammonium, the manganese dioxide, and it produces this manganese 3. Yeah, manganese 3 oxide, ammonia, and water. So that would be a complete reaction for well, this is the half reaction. The zinc and this one together. This is more common. Excuse me. This is more common. When you go to the store and buy a D cell battery or C cell or double A's or triple A's, those are known as alkaline, and they might even have it on the label. Alkaline dry cell batteries, and they operate on this chemistry. Right? These are the half cells. The cathode reaction is this one, the anode reaction is that one. And you get about 1.5 volts out of that cell. And if you need more, the device you put them in will arrange them, tell you to arrange them a certain way that will add their voltage. So maybe your device needs 3 volts. So in the device, they will be placed in series. 1.5 plus 1.5 makes 3 volts. This is a cutaway of a dry cell battery. Notice it has a graphite rod in here. The graphite rod is there just to conduct electrons. It does not participate in the reaction. The reaction takes place at the anode is the casing of the battery, which is made out of zinc, and it's covered, to protect it. And then the anode takes place at the carbon electrode, but the electrode is not a participant. The reaction takes place here, right? That's the cathode. And that's where electrons go in. Right. The electrons go in order to complete that cathodic reaction. And the source here is the zinc is being oxidized. So that's the anode. Okay. That's why when you see it marked on the battery, sometimes there'll be a plus mark up here and there'll be a minus mark down there. Or if the device you're putting the battery into, it may have little marks inside that say, this is the minus end, this is the plus end. So you know that the nipple side goes to the plus end and the dimple side goes to the negative end. Okay, there are a whole host of other types. Zinc and silver cells. Lots of times these are used in hearing aids. They're really tiny batteries. You just put them in your hearing aid and you get whatever voltage is required. These are not used anymore. Mercury cells, this reaction does work, but it's got mercury. What do you do when the battery is completely discharged? Because these batteries are not rechargeable. Well, most of them. You can still get dry cell rechargeables, but they don't last very long. I've tried it. Maybe 25 or 30 cycles, discharge, recharge, and they're done. It has to do with not just the chemistry, but the construction of the battery. Okay. So now that was an electrochemical cell, a battery. Now let's talk about corrosion. We've got a few minutes left. I think we got enough time. Yeah. Corrosion is a redox type reaction. And what we're usually referring to with corrosion is a metal is being converted to usually an oxide or a sulfide. So the metal is at 0 oxidation state. Right? That's our generic metal. And if it combines with oxygen, to produce, let's say it's, let's say it goes to a 3+ here. Oxidation state. Okay. So it's being oxidized from that one to this one. I'm just making this up. 0 to 3+. This one's -2. So in order for the oxygen, and we also have free electrons. In order for the oxygen to combine with it, it would have to be, let's see, X, like that. Now, that's not a balanced equation, of course, because I don't know what that is. I just made this up. But the thing about it is, this is corrosion, and it's a spontaneous reaction. It will occur. Most metals, with very few exceptions, do not exist as the free metal. Like, you can't find iron, well, you can, but it's rare to find iron, pure iron, in the earth anywhere. Usually it's combined with something else, like oxygen, mostly, sulfides maybe a little chlorides, or one of the halogens. But in order to be useful, if iron is that way, it's no good. I mean, it's wasted. It's corroded away. In this case, we've got a buried iron pipe. And as long as the iron remains as the metal, then this pipe serves its purpose. It's strong. It resists, it's able to transport materials in the pipe without corroding internally. But it's exposed to moisture and acids and bases and oxygen and other elements in its environment, and it will corrode over time. So how do we protect it? It's kind of like the electrolysis. Instead of letting the iron go its natural course and turn into, say, iron 3 oxide, rust, we connect it to a competing reactor. We let some other metal corrode, and we connect the two through a wire so that the electrons that are produced by the corrosion of this metal are supplied to this metal. And the reaction of this, in this case, magnesium, when that magnesium becomes oxidized, it gives up its electrons, and we supply those electrons to the iron pipe, makes it the cathode. So we keep the iron reduced here by sacrificing that metal. That's called cathodic protection. Now, the only way we can do that, and it's a little beyond this course to explain it in detail, but the reaction, the corrosion of magnesium has a much higher probability than the corrosion of iron. So this reaction is used to drive that protection. There are a number of ways we can protect the iron, right? We can wrap it in material that'll isolate it from the environment. That's possible. We can create an alloy. We can add elements into it that protect it. That's what we do with stainless steel. Stainless steel originally was 35% by mass of chromium. We just take chromium metal, iron metal, and a little carbon, and heat them up, mix them together, and that chromium protects the iron because chromium corrodes faster than iron. So if we scratch the surface, the chromium instantly converts to chromium oxide and seals the wound. And it happens so fast that even the slightest scratch is completely sealed instantly. That's stainless steel by alloy. Or we can do this cathodic protection. That's cathodic protection of an underground pipe. The buried pipe is the cathode. That's the site of reduction. We want to keep that iron reduced as iron metal. Okay, another example of cathodic protection is if you ever have the opportunity at a port of call on one or the other coast, either the East Coast, West Coast, or the Gulf Coast, and you can look at ships that are coming in and leaving, especially the ones that don't have any cargo in, they're sitting high in the water. Then it's easier to see. Wrapped around the hull is a raised belt. And that belt is made out of zinc. Zinc does the same thing for the ship's hull that magnesium did for that iron pipe. The zinc sacrifices itself to maintain the hull in a reduced state as iron. So that way, they don't get holes in their hull and sink the ship. Well, while the ship is operating and there's power, they trickle a charge into that zinc strip. They add electrons to it. So it reduces both the zinc and the iron. So that keeps the zinc from completely corroding away while there's power to the ship. When the power's off, say they're docked at port, then the zinc strip can do its job. It can sacrifice itself. And then once the ship powers back up, they can trickle a charge into that zinc and cause it to be the cathode and reduce the zinc again, plus the ship's hull. Okay. Electrolysis, we've talked about electrolysis, but there are a number of, actually, we didn't call it electrolysis, did we? Yeah, we did. Electrolysis can produce a number of different results. One is we can protect our iron hull of the ship with forcing the reaction in reverse and keeping the iron as a metallic form, non-spontaneous. In this example of electrolysis, instead of combining hydrogen and oxygen together, lighting them and watch them explode, or building them into a rocket engine, which is the way we blasted our space shuttle in space, and how many rockets now are, they have liquid oxygen and liquid hydrogen tanks in them, they combine them in the engine, and that's how they make their way to space. That's the spontaneous direction. They produce water as a product. But if we drive electric current through pure water, now actually we need a little bit of acid in there maybe to make sure the current will flow. Then we can split water into hydrogen and oxygen. And if you ever have distilled water with a little bit of hydrochloric acid or maybe acetic acid, vinegar or lemon juice, and you take a 9-volt battery and drop it in that water, then pretty soon you'll see bubbles coming off of each of the electrodes. Oxygen is oxidized. In other words, the electrons are taken from this 2- to 0. So this will occur at the anode. And the hydrogen will go from +1 to 0. That's at the cathode. And you'll see bubbles coming off of that 9-volt battery because this reaction is taking place. That's electrolysis where we actually split the molecule. Now, sometimes these reactions are undesirable. When you overcharge a lead acid battery, it produces hydrogen as a product. And if you do that, and you have an ignition source nearby, then as that hydrogen escapes and combines with oxygen in the atmosphere, you can get a fire under the hood of your car. Now they've got protective circuits built in, right? So you can't overcharge your battery, but that used to be a problem years ago. The other interesting thing is, if we ever create a fuel cell, which is another form of battery, we can use hydrogen combined with oxygen in the air and produce electric current and drive our vehicles with it. That's the holy grail of electric vehicles. Now electric vehicles are run by batteries, and batteries have to be recharged. But with a fuel cell, all you have to do is like putting gas in your tank, refill your tank with hydrogen, and you can go, right, take you 10 minutes to fill it up, you're on your way again. You don't have to sit there for 3 hours, recharge your batteries. So that would be part of the hydrogen economy. All you need is a cheap source of electricity to split water and make hydrogen. Now, there are other technical difficulties because hydrogen is flammable and it's a gas. So you got to find a way to store it efficiently in your vehicle. But there are a number of problems, but like I say, this is the holy grail. The hydrogen economy. Actually, we can move one step above that, and that's fusion reaction, but that's a different topic. So we'll let that one go for now. Okay, that's it.